about this Rodriguez for making that easy. We're going to take a look at the sun. So the sun is basically a giant ball of burning gas that actually serves our Earth with energy. And the sun, the way it works is that hydrogen is fused into helium. See, there's the isotope deuterium and the isotope tritium. They fuse together to form a helium nucleus, a neutron, and lots of energy. Now, the temperatures needed are millions of degrees Celsius. So that's why fusion occurs in the center of our sun, called the core. The sun is 109.3 Earth diameters wide, which means that 109.3 Earths can fit across the sun's diameter. And that means that it also could fit 1.3 million Earths inside of it. It itself is 10 times the size of Jupiter, the biggest planet, and we're going to talk about it next. 4.6 billion years ago, the sun formed because of a supernova. So there were these two giant stars. They each went supernova, and then the particles formed in the supernova made a disk around a giant object, and those objects just clung together more and more over millions of years, forming our sun. And our sun, as we know it, is the closest star to our Earth. And relatively speaking, the sun is able to fit about 1,300 Jupiters inside of it. It's actually bigger than most stars. Most stars are usually red dwarfs. Tiny, cool stars that live for trillions of years. We still have 5 billion years of civilization left before our sun swells to a red giant. When the sun swells to a red giant, it will engulf Mercury, Venus, possibly Earth, and maybe even up to Mars, reaching the asteroid belt. Now, the sun also has some devastating winds, which we call solar winds. Luckily, we don't feel the solar winds because of Earth's giant magnetic field that protects us from the solar winds. Only a bit can get near the poles, and that is what causes what we call auroras. Aurora borealis is probably the most popular aurora, but auroras are just formed from the solar wind. The sun also has coronal mass ejections, which are terrible. In fact, without an atmosphere, Mercury is in shock. Really, that's why it has such temperature extreme. The structure of the sun is somewhat complicated. It has a corona on the outside with almost 1,000,000 degrees Kelvin. And then you have the photosphere, which is pretty much the surface of the sun, at only about 10,000 degrees Celsius. So a lot colder, but still pretty toasty if you ask me. The photosphere can also have features on it. There are solar flares, which are really, really damaging. And there are also prominences. Prominences are kind of the little loops around the sun. And they are indeed humongous. I'm telling you, 100,000 kilometers. Almost the size of Jupiter. Which is really, really extreme. Because it's just a giant shot out of fire. Now, sunspots are black dots on the sun. And most sunspots are actually bigger than our Earth, proving just how tiny Earth really is compared to our humongous sun, which I know is tiny compared to all the big stars, like UIC and Betelgeuse. The sun is just a dwarf. Now, some of you might be asking, why don't we classify the sun as a main sequence? We kinda do, we kinda don't. Our sun sometimes is known as a yellow main sequence star, but it's more often called a yellow dwarf because of how it's so tiny compared to all those giants and supergiants. But a star bigger than our sun would be a main sequence or bigger, possibly. Our sun could possibly be the biggest size for a dwarf. As well as that, inside the sun you have the radiative zone and the convective zone. They form a cycle where the light through the radiative zone and the convective zone. The reactive zone is closer in, and the convective zone is farther out from the sun's surface. And then in the very center is the core, the place where nuclear fusion occurs with deuterium, and tritium forming helium, a neutron, and energy. Now, I know that actually fusion was the process that made hydrogen, helium, lithium, and a bit of beryllium, which quickly decayed into lithium after the Big Bang. It was after 3 to 20 minutes. It was still extremely hot, like the core of a star, but those temperatures are necessary for the atoms to actually hit each other and make a nucleus. And that is what happens inside our sun's core. At 50 million degrees Celsius, the sun's core is really, really hot. Hotter than a white dwarf. It is said that when the sun dies, after it swells, it's going to form a planetary nebula, and at the center will be a white dwarf. But that white dwarf won't be just any white dwarf. That white dwarf is going to be the sun's core. That white dwarf will have a density of 1 car weight for every tablespoon, or a teaspoon even. See, 1 teaspoon of a white dwarf, if I were to hold a teaspoon of a white dwarf, my hand would go because it would just be as heavy as a car. Nobody would try that. Well, that's it for Making Math Easy, and a reminder to stay curious in math and science.